Hello, guys, can you hear me? Our number is just very few. Can you hear me? Is that any problem about the voices? I think you can hear. Do you have any idea your friends will come or not? We are just 5 people in here. Okay, just wait few minutes, maybe they will come. Is there any lessons or course in that time? Do you have any idea? I checked the lessons. I saw you don't have any lesson or courses after 5 p.m. Okay, let's begin. I'm uploading the presentation now. Most probably we are doing our last course. Maybe next week I will do one makeup lessons for solve questions, for make some example. But most probably this is our last course. Sorry about the Monday. I had a job meeting, so I couldn't make the lesson. Sorry about that. I have to do in 5 p.m. in this day. Okay, this week we will learn about the states and finite state machines, and we will see the state tables and graphs also. Also, we will see the general models for the sequential circuits. Finite state machines is so important if you want to work with the hardware, if you want to work with, for example, the FPGA or VLSI. You have to know about the finite state machines. Almost all of the protocol, almost all of the communication protocols made from these finite state machines, based on these finite state machines. Okay, let's see. If you want to ask any questions during the lessons, please don't hesitate. Just ask. You can ask any questions. You can interrupt the lessons and you can ask any questions. Okay, state tables and state diagrams. We have examined a general model for sequential circuits. You know the sequential circuits, logic circuits. This is the circuits have memory, right? In this model, the effect of all previous inputs on the outputs is represented by a state of the circuits. All of inputs and all of outputs are represented by state of circuits. This is important. So, the outputs of the circuits at any time depends on its current state and the inputs. All of the outputs in the circuits, you have a lot of outputs in the real life. All of them depends on its current state and input. These also determine the next states of the circuits, the relationship that exists among the inputs, outputs, present states, next states. You know this presentation, right? You know what's the means of the present states. You know what's the means of the next states. They can be specified by the either state tables or state diagram. You can use both of them. State table, I think the easier way is the state diagram. It depends on you. Maybe you can find the state table the easier one, but in my guess, the state table diagram is the easier. So, state table representation of a sequential circuit consists of the three sections labeled present state, next state, and output. You know the tables. You know the tables in the logic, and you know what the label means. You have present states, you have next states, also you have output. The present state designs the state of flip-flops before the occurrence of the clock pulse. The next state shows the states of flip-flops after the clock pulse, and the output sections list the value of the output variables during the present states. You know the clock pulse, right? You know the flip-flops. In the flip-flops, you see the inputs on the outputs. But when? In the rising edge or the down edge, you know the clock pulse. Every clock pulse, you get the results in the flip-flops. State diagram, in addition to graphical symbols is a much easier way to understand any problems, tables or equations. Flip-flops can also be represented graphically by a state diagram. In this diagram, a state is represented by a circle, and the transition between states is indicated by direct lines or arcs. We will use arcs a lot. Also, we will use the direct lines connected to circuits. You will see this, what's the circuits, what's the connection between the circuits. Okay. Just look at the example. There's a states, you know, the initial states is 0, 0. There's another states, another states, another states, and there's a connections. The binary number inside each circle identifies the state of the circle represented. You can understand from these graphs. Every circle is the states. Every circle identifies the states. The direct lines are labeled with the two binary numbers separated by slash. We will see that what does it means. There is two numbers in here. For example, 1 1 0 0 1 0. What do they mean? The input's value that causes the state transition is labeled first. Okay, the first one is input. First one is input. The number after the slash symbol gives the value of the output. The second one is the output. Okay. There is a state, there is an input, and there is also output. For example, the direct line from the state 0 0 to 0 1 is labeled 1 0. You can see from that. You can see that from this. For example, the direct lines from 0 0 to 1 0 is labeled 1 0. That means if you are in state 0 0, this is the idle, this is the first state, for example, and if you have a 1 in the inputs, if you get a 1 in the inputs, you should go the next state is 0 1, and the output will be 0 0. The directed line states 0 0 to 0 1 is labeled 1 0, meaning that if sequential logic is in a present state and the input is 1, then the next state is 0 1 and the output is 0. Do you understand these parts? I hope you understand these parts. If in the beginning you are in here, you are in the 0 0 state, and you have the input, right? If you get the 1 in the input, and also if you get the output is 0, you have two choices, right? You can get 1 or you can get 0. You have 1 bit input in the circuit. There's a circuit in here, just kind of you can think about the box, and you have 1 bit inputs, you have 1 bit output. So you can get 0 or you can get 1 in the input, right? If you get 1, you have to get the next state 0 1. Just depends on if you read this graph, you can see that if you get 1 in the inputs, and you can go the 0 1 states, and output will be 0. If it is a present state 0 0 and the inputs is 0, if it is in a present state 0 0 and the input is 0, it will remain that state. You can see that it is remains the same state, right? You don't change the state in this case. In this case, you don't change the state. If you got 1, you change the state and you go to the next state is 0 1. If you got 0, just remind the state. This is just example, by the way. This is not the rules. This is example. I draw this state diagram, and we are just learn how we read the state diagram. In this slide, we are just learn that how we can read the state diagram. Okay. A directed line connection, a circle with itself, indicates that no change of state occurs. The state diagram provides exactly the same information as the state table, and it's obtained directly from the state table. You can obtain the state diagram from the state table. Okay. So there's an example. Consider a sequential circuit shown in the figure. There's a figure, you can see that. It has one input X. The circuit has one input X, one output Z. You have one output in here, and two state variables, Q1, Q2. So having four possible presents, right? You have two state variables, Q1, Q2, you have two flip-flops. That means 2 power of 2, this is presents 4 possible states. 0, 0, 0, 1, 1, 0, 1, 1. You don't have to use all of the states. You have to decide that how many states you need, and you can use just how many states you need. Okay. The behavior of the circuit is determined by the following Boolean expression. These equations can be used from the state table. Suppose the present state is 0, 0 and input x 0. Under these conditions, we get z0, d1 1 and d2 equal 1. You can write these parts from the circuits. You know the flip-flop, you know these gates also. So the next state of the circuits D1 and D2 equals 1, 1. And this will be the present state after the clock pulse has been applied. The output of the circuits corresponding to the present states 0, 0, x equal 1 and output is 0. This data is entered into the state table as shown in the table 2. We will show the table 2 in here. You know that, right? If there is a flip-flop, it means there is a memory in the circuits. If in the circuit there is a flip-flop, that means the circuit has the memory. So circuit is the sequential. And in that circuits, you have present states and you have next states, right? If you use the flip-flops in the circuits, so that means you have present states, also you have next states. Okay, you can say this one, set equals x and q1, not x or q1, and you can write this expression from the circuits. So you can write this table. This is a state table, and also there's a state diagram. So how can we write the state diagram from the state table? Let's see that. You have two possible inputs. There's a present state 0, 0, 0, 1, 1, 0, and 1, 1. If you are in the 0, 0 state, and if you get x 0, you can write from this equation. You can use this equation. So the next state will be 0, 0. If you have x 1, next state will be 0, 1. Okay. So you are in the 0, 0 states. If you get x1, let's see that. Let's do that. Q1 is 0, right? And x also, if you got x0, 0 and 0, that means 0. Let's see d1. Not x is 1. So q1 is 0. It means d1 is 1. Let's see d2. X is 0. Not q2 is 1. Not x is 1. Not q1 is 1. Because q1 and q2 is 0, right? We are just looking at this state. So what is this equal? What is this result? Is 1, right? So next state will be d1 and d2, and it will be 1, 1, right? And output will be 0. Output is z, right? Next state will be d1 and d2. And if you got the x1, you can get these results and these results. Do you understand this state table? Do you have any questions about the state table? You can say that I don't understand anything. Can you please can you please explain the state table again? You can say that. Or if you have any confusion, if you have any mistake, you can say that. Do you understand this part? This part is important. Do you understand how can we read the state table and how can we write the state diagram, state graph? Okay, I consider you understand. And you can write this state graph, right? First time it was in the 0, state. If you got 0, then the results will be 0, 0. This one is input and the output. And next state will be 1, 1. Next state will be 1, 1. In 1, 1, if you get 0, if you get input 0, so next state will be 1, 0. It will be 1, 0. If you get x1, next state will be again 1, 0, but the result will be 1. This part result will be 1. This part result will be 0. Okay, and you can write this graph from the state table. Okay, and there is a more example. I hope you will work with this table. I will share the presentation and I want from you just work with this table. Maybe in the final exam I will ask this SRGK flip-flop and I will ask you to just write the state diagram from the table, from the truth table. You can write the truth table with present and the next state, and you can draw this state diagram from the state table, right? You know the flip-flops, you know the flip-flops table, and you should draw this state diagram from the table. Maybe in the final exam I will ask them. Okay? So there is a two kind of finite machine. There is a two kind of finite state machines. The Mealy machines and Moore machine. If you look at this two diagram, can you say what is the differences between them? First thing, you have to see there is an input connection. In the Mealy machine, outputs depends on inputs and the state. Outputs depends on inputs and also depends on state. But in the Moore type, output only depends on the state. Okay, let's see that. Let's see more information about the Mealy and Moore machine. Mealy machine output depends both on the present state and the present inputs. Output depends both present state and present inputs. In the Moore machines, output depends only upon the present state. Generally, it has fewer states than Moore machine, and there is vice versa. It has more state than Mealy machine. The value of the output function is a function of the transitions and the change when the input logic on the present state is done. The value of the output function is the function of the correct state and the change at the clock age and whenever state change occurs. MIDI machines react faster to inputs. They generally reach the same clock cycle because the outputs depends on the inputs, also the present state. In the Moore machines, more logic is required to decode the outputs, resulting in more circuits delay. They generally reacts one clock cycle later. Okay, let's see example. This is the easy way to understand the state machine. We will do a lot of examples. The specification, the circuit will examine the string of zeros and ones applied serial once per clock to the X inputs and produced only when the prescribed output sequence occurs. Any sequence ending with 0 1 0 1 will produced and output will be 1. Coincidence with the last one input, the circuit doesn't reset when a 1 output occurs. So whenever 1 0 1 is in the data stream, a 1 is output coincident with the last one. Okay. You have serial inputs. In this example, you have serial inputs like that, and serial outputs, and you got some data like that. This is just a random data. If you get this one 0 1 0, then output will be 1. Otherwise, output will be just 0. This is a kind of communication protocol. Okay, you have serial, for example, this is just an example. You have serial inputs X, you have serial outputs. If you have this part 1 0 1, then Z will be 1, otherwise will be 0. And there's another example, 1 0 1, Z will be 1, 1 0 1, Z will be 1. Otherwise Z will be 0. Okay, this is the easy one. This is the general examples. It calls sequence detector. Okay, start construction of the graph. Choose a starting state and a meaning of that state. The starting state is typically a reset state. This is the idle state, kind of idle. Here, meaning of the starting state can be the system has been reset, and this is the initial state. This is the idle state, this is the initial state. A sequence of 0 or more, 2 or more zeros has been received. 2 or more zeros has been received. Okay. In the beginning, you are in the S0, state 0. You have to catch 1 0 1, right? You are getting the serial inputs. If the inputs will begin with 0, you can just remind the same state, right? Because if the input is 0 0 0 0, you don't have to do anything until you get 1. Because if you get 1, there's a chance you can get 1 0 1, and you have to act. Okay, you have to go next state. Now, meaning a sequence of the 0 0, you don't know how many zeros in the input, you're just waiting for 1, has been received when coming from the state 0, and the first one has been received. First one has been received. This is the input. This is the 0 0 0 for example, and the inputs, and what will be the output? 0, 0, 0, and again 0, right? Because you don't get still 1, 0, 1. And next state will be state 1, S1. What happens when S1? A 0 input causes a transition to a new state 02 with the new meaning, and a 1 keeps you in the S1 where the first one of possible 101 sequence has occurred. For example, if you have 0 in the input, 0, 0, 0, okay, how many 0 you don't know, and you get 1. If you get 1 again, you cannot get 1, 0, 1, right? You have to wait for the 0. If you get 1, you don't have to do anything. You can remain S1. If you have 1 in the inputs, you have to wait for 0. Right? This is the protocol. You decide that. You decided that if I send the 1, 0, 1, then catch the data. Otherwise, don't do anything. You catch the first one, but you have to wait for the 0, right? If you had the 0, then you can get the new state. If you get 0, output will be 0, 0, 0, 0, 0, also 0. So 0 because you don't have 1, 0, 1 yet. So you can go the next state, 0, 2. In the state 2, 1 arrives. How now we have sequence of the, we are in state 2 now, right? You begin with state 0, you go to state 1, and you are, for example, in the state 2. In the state 2, if you get 1, so you have the first one of the new sequence, and your sequence is completed 1, 0, 1, and output will be 1. Now I have a sequence of the 0, 1, 0. If you got the 0 in the inputs, so you can get 1, 0, 0, right? So you have to go back to 0, state 0, right? For example, you are in here. Your input is 0, 0, 0, and 1. You got S1. 0, you got S2. If you have in the input 0, so you have to go S0 because you have to wait another 1, right? You can catch the 1, 0, 1, so you have to go S0. If you got the 1, so you can go the S1 again. For example, this one. You can see from that. You can get 0, 0, 1, 1. If you get 1, so output will be 1. And 1, 0, 0, you have to go to state 1 in here, and state 2 in here, state 0 in here, state 1 in here, state 2 in here. And if you get the 1, so you can go back to state 1, and output will be 1. So if you get again 0 and 1, you get another 1, right? And there's another one in the output is 1 and 0, 0. Okay, this is a basic state diagram. You can see from that. Do you have any question about this state diagram? You can ask me to tell all of them again. You can ask me to explain all of them again. Is there any question? Okay. Another example. For example, you have again the serial input and you have again the serial output. If you catch, there's another sequences. 0, 1, 0. This is another example. Or 1, 0, 0, 1. When a sequence is detected, output Z will be 1. Otherwise, Z will be 0. For example, this one, right? For example, you get 0, 0, and 0, 1, 0. You catch that, and output will be 0. And you catch another, output will be 0. You catch another one, this one. This one also you can get 1. This one also you can get 1. Also this one. Also this one. You have two conditions in here, right? If you got 0, 1, 0, or if you got 1, 0, 1, you will get in the output 1. Otherwise, output will be 0. Okay. Okay. In the rest state, in the idle state, will be S0, have no inputs yet. Then if you have a 0 inputs and the outputs will be 0, transition will be S1 if you get 0, because we are waiting for 0, 1, 0. We are waiting also 0, right? We are waiting also 1. Both of them you have to change the state. You cannot remain the same state in this example, right? Because if you get this one, Z will be 1, or if you get this one, Z will be 1. That means 0 also 1 is useful for you. You can check 0, also you must check 1. Okay, next, for example, you state S1 and S2. Okay, let's see. Let's say that S4, because you will see that why we call the S4 to S2. There's a state 0, state 1, state 4. State 0 is reset, is kind of idle. It's kind of start state. And S1 is 0, but not 1, 0. S1 is also you can get input 1, but not 0, 1. This is two possible conditions. If you get 0, so call the S1. If you get 1 in the S1, it was 0. It was, if you get 1, so you can check S2, right? Also, same for the S4. Let's see the results of this. Let's see this diagram. You can look at that. There's a initial, there's an idle state, there's a S1, there's a S2. If you got 0, you should go S1 and output will be 0. If you got 1, then you can go S2 and output will be 0. If you get 0, you can go S3 and output will be 1, right? Let's check this also. If you get 1, you can go S4 and output will be 0. This is the input, this is the output. If you get 1, go state 4 and output will be 0. If you get 0, state 4, output will be 0. If you get 1, just go to state 2, because if you in state 2 and you get the input 0, you can get 1, right? This is just kind of the state graph. State graph depends on you. You can do a lot of exercises. You have to do a lot of examples. and then you will get used to it, and you can improve your state graph like that. You have to think about every possible input. You have to think about every possible inputs, okay, and you will get this final graph in this example, because you are looking for 0 1 0. Also you are looking for 1 0 0 1. If you solve this graph, let's see that. Let's solve this graph. In zero state, in the initial state, you can get 0 or you can get 1, right? There's the inputs, there's the serial inputs. You can have two choices. You can get 0 or you can get 1. Okay, two possible conditions. In the 0 inputs, you have to go S1. In the 1 inputs, you have to go S4 in this graph. So, if 0 again, you have to remain S1. If the 1, you have to go S2. If there is also another 0, you get the 1. If you have another 1, you have to go these parts, because you can get this. You can consider that this part is looking for 1 0 0 1, and this part is just kind of looking for 0 1 0. Okay. Those state machine we just looked, those are the mealy state machine, because we are just looking for inputs, also state, right? In the first example, we are looking for 1 0 1, right? And we are looking for inputs and also states. But in the Moore machine, you only checked the state, and there is a just different representation. There is one this parts state where you have received a non-middle 0 or a long string of zeros. Output is 0. Output is identified within the state, not on the transition. Okay, there is a just differences between the presentation. In the Moore state, you don't use the inputs in here, just for looking at the outputs. Just say that. Let's look at the same example. We did this example in mealy machine, and we got this result, right? In the mealy state machine, we got this graph. Just look at the Moore. What about the Moore state machine in the same example? Okay, there is a S0 in the first state 0, and the output will be 0. If input 0, output will be 0. If input will be 1, next state will be state 1, and output also 0. On a 1, have the first one of the sequence, state S1. On a 0, now we have the sequence that, and in the 1 0, so define a new state, state 2, and transition to it. In the state 1, if you get 1 again, you have to rewind the same state, and your result will be remain 0. If you have the 0, then you must go the next state 0 2, and your output is still 0. Okay. And in the state 2, if you get 1 again, then you get 1 0 1. Your output will be 1, and you will go to the next state. If your next input will be 0, then you have to go state 0, initial state. Transition from S2 0 input back to S0 1 input. What is the sequence? Go to the new state S3, which output is a 1. The S3 output is a 1, right? So in the S3 have received input sequence that ends in 1 0 1. So next input, if you got 0, end of the sequence. If you got 0, you can go to S2 back, because there's a 1 0, so back to S2. If you get 1 in the input, back S1. You can go back to S1. So you have 1 1, the first one, just like you get the first one. And there's a state graph. You can get the Moore machine. This is the same, right? In the Mealy machine, there is the same results in here. There's a Mealy machine. There's a Moore machine. All of diagram, our gate gets you the same results. There is no differences between them. Only the represent part is the difference. All of part is the same. Okay, we done our last course. I considered I thought you ask some questions about the state machine, but nobody asked anything. I think in the last few weeks, nobody asked me anything about the lecture, or nobody asked me anything about the courses. When you study the final, please mail me, and you know my university mail, right? Right, my university mail. This is the university mail. You can mail it. If you have any questions about the lecture, if you have any questions about the courses, please let me know. Maybe I will do a makeup lessons. Maybe I will do a makeup lessons for the solve examples, some example for the final exam. So I have to finish these courses in here. Thank you to Mohammed. Thank you guys. Have a nice day. State machines are important. I hope you will work with them. If you have any questions, please mail me. I will explain all of them again. I can explain all of them again. I want to know you understand the state machines or the flip-flops. Those two parts are important. Abdel Rahman, you can't see the grade of assignment. Okay, I will look at that. Just mail me. Can you mail? It will be great. Mail me about your grades and I will check them. Have a nice day, guys. Maybe I will send the homework. I don't know. Just work well, study well, the final exam. Okay, see you guys.